I'm going to be talking about the Mantapay Protocol and some of the new techniques that we've used to simplify it and to get some cool new features. So just an overview of what our protocol is trying to accomplish. So if you consider using a public ledger protocol, you can have people who watch the blockchain and can listen to people's transactions and can learn about their spending history and can figure out things that probably aren't something that you want to reveal publicly about people. Like you don't just want people's wallets to be just out in the open like that. So the goal is to find a way to design a ledger so that we can hide the amounts and recipients of transactions, even if someone is watching someone's network broadcasts. So there are two properties that we want to ensure that we preserve when we build a ledger that has privacy as a fundamental component. So the first one is obviously that any transaction can't modify the total supply of an asset, that you can't create or destroy new tokens. And when you transfer something, you actually need to revoke your right to spend it again later. So this is the double spend problem. And the other thing, which is the privacy part, is that when you read the ledger, you can't learn any information about any transaction and any existing user balances. So these two properties sort of seem to be at odds with each other, because you want to verify that any transaction preserves the total supply of the asset, but then you have to learn what the transaction amounts are, because otherwise how would you do it, right? Well, actually there's some technology that exists now that lets you get away with this, and this is some clever cryptography that I'll talk about. Also for this talk, I'm not going to be talking about the public side of the Mantapay protocol. Mantapay also includes a public ledger, which you can merge, assets between public and private. But I'm just going to focus on the private part. Yeah. Okay. So the new protocol, we wrote up a spec. It's not fully finalized, but it's something that you can all take a look at if you'd like. And of course, feedback always welcome. And so I'm going to be talking about just not extremely technical version of the protocol to try to make it approachable. And so we're going to be viewing the transactions from different levels of abstraction. And at the end, we'll look at a general version of the protocol for any number of senders and receivers. So initially, we'll just talk about one sender, one receiver, and we'll see how it generalizes. So we have three different participants that we'd like to model. First is Alice. Alice is the sender, and the sender represents someone that has access to some assets that the ledger has guaranteed them their ability to spend. Bob is a receiver, and they are the participant that is going to be guaranteed the ability to spend something in the future after a transaction has occurred. And the ledger is responsible for validating this, and also will store all the public information involved in any transaction, for the lifetime of the blockchain, as long as people are still using it. So the first thing we're going to talk about is the send part of the transaction. So the ledger, you can think of it as like a database, and like any sort of get request system. You send messages to it and you receive messages from it. So what kind of messages would you send to the ledger to perform a transfer? So the way this works is you build something called the ephemeral key, which is this gray box in the middle. And the ephemeral key represents a transaction, and it represents the secret that Alice will create so that the transaction will go through and no one will learn anything about the transaction. So how do you build this secret key? You take Bob's public key which is something that he shares with Alice or shares in public, but not necessarily. He can just only share with Alice if he likes. And you use an entropy source to add some randomness to it. And you use the current state of the ledger to pin this key to the current state so that you can't use it again later. And then Alice will use this secret key and also her own secret key to build a new hidden asset, which I'm going to denote with the question mark. And then she will send this whole package that she builds, which we'll talk about how she builds it. She'll send all this thing to the ledger, and then the ledger will verify it and accept it or deny it. So then how does Bob receive the ability to spend the asset? So what Bob will do is Bob will listen to the ledger, and every now and then the ledger will receive messages which will have all these new coins in them, which are hidden. And so Bob will ask the ledger, give me the most recent coins that you've gotten. And Bob will then use his secret key, which derived the public key that he gave to Alice earlier. He'll use that key to scan through the coins and try to unlock them. And if he can unlock them, then that means that they're his. And so then he can save them in his database that he stores on his computer, and he can use them later to spend. But because the ledger, will outlast Bob, he can always just query it in the future if he forgets to save his coins. So there's a property that most crypto wallets have, like the crypto designs have, is that once you know your secret key, you should be able to restart your wallet anytime and still be able to access everything. So just from your secret key, you should be able to derive everything that you own or that you spent or whatever. So,
hey Brandon, I have a really quick question here, and it's more so a point of clarification. So what you're saying is that when you use your secret key to find these coins and they get the I guess that gets stored locally, you can requery at some other point with the same private key to get those coins again, right?
Yeah. So when you're unlocking them, it shows you like your different spending options. So like, let's say you were sent like 3 different coins. You can always unlock them at any point. It says, okay, yeah, I have these 3 coins now. Whether you can spend them or not is a different question, because if you've already spent one, you can't spend it again.
Yeah, gotcha. Okay, so you can query anytime and get the amount that you have essentially, but you can only spend the unspent.
Right. The amount is sort of something that you calculate on top of you can query it and get all the coins you've ever received over your entire lifetime of the wallet. And then there's the subset of those that are still spendable, right? And that represents your balance.
Yeah, understood. Thanks.
Yeah, okay. So this is the receive protocol. So now how exactly does this unlocking happen? So the way this works is this uses a hybrid encryption scheme. So first we'll talk about what Alice does to encrypt the asset. And the way this works is that Bob derives a public key from his secret key, and he does not reveal the secret key. The key is later used to spend the assets, like I said. And then Alice uses Bob's public key and this ephemeral key that she built earlier to encrypt the asset. And the way this works is using a few different technologies here. So you use elliptic curve Diffie-Hellman to derive a shared secret, capital K, and then you use Blake 2s key derivation function to get K star, and then use symmetric encryption, AES, Galois counter mode, to encrypt the asset. And then also you derive this public ephemeral key, which is then used to decrypt the asset. Also, for reference, the dotted line will refer to things that Bob knows about or things that Alice knows about. So Alice knows everything on the right, and Bob only knows things on the left. Okay, so this encrypted node, if you see on the right here, it has these 2 pieces. It has the encrypted asset, and it has this public key, the ephemeral public key. So if Bob receives this, how does he decrypt it? So it decrypts it again, same thing, it's just the reverse. No, it's not the reverse, but it's this is like the only way to do it. So you do elliptic curve Diffie-Hellman to create the shared secret again, capital K, and then use Blake 2s, K star, and then you decrypt it. So that's all nice and all, but how does that let us actually spend the token? So the way it works is that for Alice to spend her token, she needs to present a certificate, which we'll refer to as CMA, and that's called the unspent transaction output. And this represents the fact that Alice was on the receiving end of an asset. So at some point in the history of the blockchain, Alice received a token, and the token comes with a certificate. And she needs to prove the ledger that this UTXO has been seen before at some point. If it's just a fresh one, that means that Alice is creating her own certificate, and that means that nobody gave her the asset, which is not correct. So it needs to come from somewhere else. So to transfer the asset to Bob, Alice will generate a new UTXO on his behalf, and this is called CMB. And she also create a void number, which represents the revocation of her right to spend with CMA again. So CMA was given to her by the previous owner, and then she'll create CMB and void number, and void number will void CMA, and CMB will become the new location of that token, basically. So the ledger, to keep track of this, will store a set of UTXOs and void numbers and keep track of which ones are there or not. And it needs to ensure that it never sees the same UTXO or void number twice. If it sees the same UTXO twice, that means like you've sort of created the token twice. And if you see the same void number twice, that means you sort of spent the token twice. So neither of these both of these will violate the total supply invariant, which we talked about earlier. Also, that thing the encryption decryption protocol that I talked about a minute ago, is called the in-band secret distribution. Okay, but how can Alice create CMB on Bob's behalf? So the way that she does this is you compute another shared secret called the trapdoor. And this uses the same technology as before, this elliptic curve Diffie-Hellman, to produce something that both parties can produce this number using different keys. So in this case, Alice will use the ephemeral secret key and Bob's public key to create the trapdoor, whereas Bob will use his own secret key and the public version of that ephemeral key to create the same trapdoor. And the way that works is with the Diffie-Hellman protocol. And once you both have the trapdoor, you can then use the Pedersen commitment to commit the asset with the trapdoor. And this ensures that because the trapdoor is the same and the asset is the same, because Bob decrypted the asset from the encrypted node, then the commitments will be identical. So this way, Alice can generate the commitment and then post the relevant information to the ledger so that Bob can later produce the same commitment to prove that he can spend the asset that Alice created for him. So now Alice needs to generate the void number. And there's also another part. She also needs to verify that the commitment that she received from the previous owner still belongs to the ledger. So the void number is generated very simply. It's a commitment. It's a commitment of her secret key and the trapdoor. Now, note that this trapdoor is not the same trapdoor we saw in the previous slide. This is the trapdoor of the transaction before that. So when Alice received the asset, there was a trapdoor associated with that. That's the trapdoor that she uses to generate the void number. And this trapdoor ensures that the commitment and the void number are linked together so that she cannot create a void number out of nowhere. The point is that the void number is supposed to void the old UTXO. So it needs to be the same trap, it needs to be connected in some way. And the way that we chose to do it is to use the same trapdoor. For Alice to prove that she can actually spend with the CMA, the commitment, she'll need to prove that it belongs in the UTXO set of the ledger. And the way this works is using a Merkle tree, and you can generate a proof, a membership proof in the Merkle tree. The Merkle tree is just it's a data structure, which is like a set, a data structure, but it also has membership proofs that can be verified independently of the set. So the set can exist somewhere, and the membership proof can be verified without access to the set and without access to the element which you're proving the membership of. So Alice will generate this proof, and then we'll see later how she uses this proof to convince the ledger that the commitment was actually seen before. So the way this works is that if you look on the left here, you have all the data associated to the sender side of the transaction, which is Alice, and everything on the receiver side, which is Bob. So you have all this data here, and we've described how you construct it using all these different primitives, like elliptic curve and commitments, and membership proofs and Merkle trees. And the point is that a lot of this involved a lot of secret information. And if this kind of information was made public, it would invalidate the entire thing. So how do we, and this goes at that central problem that I talked about at the beginning, which is you want to validate something, but you can't reveal any information about it, or else the privacy isn't even there. So how do you do it? So the way you do it is you use a zero knowledge proof, and this is something that's extremely powerful and is at the underlying of the entire protocol. Without it, it would be impossible to do this, most likely. So the way that we do this is we go through this entire process that we've gone through to compute all these different quantities, but we do them in something called in circuit. And what that means is that you generate basically like it's sort of an embedded language in whatever you're working on. And it's like there's a compiler and there's a interpreter, and you basically redo the entire computation in this other world. And at the end of the day, the thing you get out is a proof, and that proof can be verified by someone else who isn't you, and they can be convinced that that the proof is correct without knowing anything about the actual things that you computed with. So I'm not going to really give an overview of zero knowledge proofs here, but the point being is that you can verify that the entire construction we've done so far is correct for any given examples of these values without revealing what those values are. So Alice will use this zero knowledge proof to prove that she had the ability to spend the asset, which was the CMA and the pi A. Bob will have the ability to spend it in the future, which is CMB. Alice will not have the ability to spend in the future, which is VNA. So once you prove all these things, then the ledger can be convinced that the invariants are preserved, and it should accept the transaction. What else? Oh yes. So the ledger will also need to verify that the void number and the commitment have not been seen before, and should reject it if they have. So the way that it works is that Alice will send the zero knowledge proof and will also send VNA and CMB, not CMA, and those will be stored on the ledger. And that's fine because those are public. Those two pieces of information are not, they don't reveal anything about the transaction. So if the ledger follows this protocol, then it can be assured that Alice and Bob cannot break the total supply invariant by doing some crazy random transaction that tries to break it. Alice and Bob can still de-anonymize though. So this is something the ledger can't prevent anyone from doing. You can always reveal your hand, but if you don't want to, it tries to not make it possible for anyone else to reveal your hand for you. So in general, this is the protocol. On the left, you have senders, which are a combination of 6 pieces of information. And on the right, you have receivers. I here is the index of the receiver. So receivers come in a certain order. You can say like you have 2 receivers and you just mark one of them as the 0th one, one is the first one. And if you construct those things in the, if you construct the void numbers, commitments, etc., and you prove those in circuit, then the ledger will be convinced that it's a correct transaction. And the only final thing that's different from the one-to-one protocol, so you have to prove that the sum of the input assets is equal to sum of the output assets. Yeah, that just means that it's more flexible. So you can, like, if you have 3 different, if you have, let's say you're doing a 2-to-2 protocol, then you can do like, let's say you have 10 units and 3 units, then you can combine them into 12 and 1, for example. And 12 can go to one receiver and 1 can go to someone else. But that's not that important for this. Yeah, so any questions?